This tennis ball is bouncing. I'm going to answer the questions. Is this relationship better modeled with a linear function or exponential function? You're going to justify that with data. Also, the tennis ball needs to bounce between 53 and 58% height. So you're going to say whether this tennis ball meets those requirements. You're going to write an equation that models the bounce height for each bounce. And then you're going to tell me how many bounces it will take to be 1 centimeter or less. So you're going to answer these four with your partner. Number one, let's take a vote. Who's thinking linear? Okay. Who's thinking exponential? Yeah, so here's what I saw when I looked at number one. I saw divided by 2, divided by 2, divided by 2, divided by 2. I'm saying general. I know it's not exactly divided by 2. In fact, if I had to go percentage, maybe 0.53 over and over is close-ish. So I'm going to use that data. To be linear, what would need to be happening point to point?
It would need to be constant.
A common difference that is constant, right? So right now it's like minus 70, minus 40, minus 20, minus 10. That's not constant. There's no slope there. It can't be a line. So that's why an exponential function is the better model. Then, if you found those, most of them were about 53%, which gives a little wiggle room. I said yes, almost always 53-ish percent. And I got that by doing 80 divided by 150, 43 divided by 80, 20 divided by 43, and 11 divided by 20. Okay. There was one that was like 48, 49, but it was just one of the bounces. So you could talk about that, say, no, one of them was below. Do you know who would like this underinflated ball? TB12. Okay? Hey, I'm a TB fan, but we all know he likes a deflated football, but I'm a fan still. Now, let's work at making this equation. So height, h equals, what comes next in my function? We've been doing this for a little while now. 150. And what is 150 in context, everybody? The starting height. So the next number, you just got to be close. One time today I used 0.53. Right now I'm vibing with a 1/2. But earlier today I did write, let's just write them both. I did like a 0.53. Remember, it wasn't a perfect, it was just close-ish. Yeah, Brandon.
I did 8/15.
Okay, yeah. So close-ish, right? If it's a model, there's a little more wiggle room to just use something nice and easy like a 1/2. Now, to get down to that 1 centimeter, I think it took me 8. So I just used my function, and that got me about 0.9. So I knew the 7th bounce was more than a centimeter. The 9th bounce was less. Can we have a partial bounce? And I did this earlier. You can't see this in the video, but I'm going to drop a ball. Let's count how many times it bounces before it's like 1 centimeter is like only that, right? So 150 centimeters is like 1.5 meters.
Yeah.
So like 4.5 feet. Is that right? Ish.
It's never gonna get that high.
Let's count.
That BB got
1, 2, 3, 4, 5, 6, 7. It's probably pretty close.
Probably separated.
Yeah, but this isn't a concrete floor. This carpet messed us up. Also, I threw this ball as hard as I could at the door earlier today, and that probably took a little air out. But pretty close.
Really?
Pretty close. It was kind of fun to just do it and have it be pretty close. All right. So we're going to look at some other bouncy balls next. And I'm going to give you the data. So there's going to be 3 bouncy balls. The one we already did. So keep that. It's going to be similar to that, actually. Then 2 more. Your job. Which one's bounciest? That's a real word, bounciest. Okay, which one's least? Explain how you know. You're going to write functions for all of them. You are going to write equations for all of them, those functions. And then you're going to answer the follow-up question. Let's get you the data. So you'll need to keep the other, oopsies. I'm going to have to take a picture of the data for you. You're going to need to keep this page up in your notes. And I need to get you guys the data sheet using my cane line. I just put it on the dot cam in the other classes. There you go. There's your data. Let's get after it. So, you're going to reference your table with me as I get to the questions. The table complete. Which one is the bounciest and how do you know, Vinny?
Ball B.
Yeah, ball B. And how do you know?
Well, because all of its reads are larger and it's at a higher.
It's at every bounce it's more, right? Also, if you found its decay factor, I believe it was 7/10. Was that one 7/10? Okay.
Yeah, that's what I mean.
Which one was least bouncy? Who can tell me and how they know? Sean?
C.
C was least. And did you get the factor for that one?
4/10.
Yeah, I got 2/5. 4/10 is 2/5. So, of course, if it's losing 3/5, that's more loss than 3/10, right? So, less bouncy, least bouncy, most bouncy. So, for each one, let's write the function. The first one, we kind of already had, right? Let's call it f of n equals 150. What was our decay factor for the first one?
1.
About 1/2 to the n. For the second one, I'm going to call it g of n. It also started at 150. And that decay factor we already wrote down was 7/10. And then the last one, the least bouncy, I'm going to write it up here just because this is where there's room. H of n. It started at 150. Decay factor of 2/5 to the n. So, how could we tell just looking at the equation which one's most bouncy? Ryan? Yeah, this shows the least decay. So we could look, again, we look at multiple representations all the time because that's good communication, right? In language arts, you write a paragraph with support. In mathematics, we have multiple representations that say the same thing but with support. Last, if they drop from 300, the bounciest one from 300, how would it change my function? Who could tell me? If I change my height to 300, how's it going to change my function? Ivy? Yeah, instead of g of n equals 150, I'm still going to have the same factor of decay, right? So the only thing that's going to change is my a value in my exponential function. Cool. A is the starting value every time. The y-intercept, the vertical axis. It has many names. Next up, we have an incomplete table. There is another bouncy ball. There's so many bouncy balls. You know where it's at after 2, but you do not know where it started. You're going to use some mathematics to backwards generate the 0 and 1 bounce. Then you're going to write the function. Then you're going to look at graphs A and B and say which one represents the situation. And answer question 5 with your partner. Let's go. I'd like to figure out what these first, where it started. So who can tell me their process they used to backwards generate values here? What did you do to backwards generate? Ava?
I found the rate of change between 2 and 3 and 3 and 4.
Whoa. I hit stuff on my bad. Okay. So 2 and 3, and what was that? So to go from there to there, you kind of had to multiply by what?
I just divided this thing by 2 and 4 by
To go from here to here and here to here?
to get like the percentages.
So what kind of change did you get one thing to the next?
Well, I got all the way down to but for the first one, I think it was just at 70%.
7, yeah, so I got 7/10, which is 70%, right? So then, what'd you do with that information to go this way?
Then I just did
Oh, I love what Ava did because it's not what I did. So Ava said she reestablished this as 0 instead of 2. You guys hearing this? Wow, Ava, this is the first time this has been said today. And it's like smarter than what I did, I feel like. Or if I were to redo it, I might do it your way instead of my way. So, what Ava said she did, she reestablished this spot as 0 and wrote the function y equals 73.5 times the growth factor of 7/10 to the negative 2. And that pumped out what? 150, and this one's 105. That is awesome, Ava. Anybody else do that? Because that's the first time I've seen it today.
I did it.
Yeah. Even if you didn't do it, everybody see that negative 2 takes you back 2 steps? Okay, I'll tell you how I did it. Nowhere near as fancy, and actually more work. I divided by 7/10 twice. So
What?
I did divided by 7/10 to go back. I got that and divided by 7/10 to go back. I could have just one shot it. That's cool. Guess what? Since negative exponent means reciprocal, this is dividing by 7/10 twice too. We did the same thing,
Oh, like that.
only different. Man, my mind is blown.
Same here.
Okay,
Good job, Ava.
let's get this now.
Awesome.
Now this equation's kind of like all we have to do now to make the equation is the height is equal to what we now know our original height was 150 times the decay factor of 7/10 to the n power. Which graph is better? Raise your hand for A. Raise your hand for B. I've got B. And the reason is the x value is the number of bounces. Can we have a partial bounce? No. So what I've had people
You can't have partial children.
what I've had people think of all day today is we've seen the ball bounce where we have time and height, and that looked like this and was continuous, like one of those things. That would be continuous. So it's because our x is bounce, we don't have partial bounces. So 1 bounce is this, 2 bounces this, 3 bounces has to be that. So it has to be B. And then the nth bounce, theoretical nth bounce. Will they ever be lower? Not ever lower. Cuz it starts the same and decays less. Now, less. Now they will, in practical terms, be the same at some point when they both stop bouncing, right? Like there's a theoretical height of bounce, but then we know like it would just stop bouncing at some point. Then they would be the same, but never lower than still, right? That's kind of cool. Kind of cool to think about. You think that bouncy one's talking smack, be like, you're never going to be bouncing as high as me. That's how you all sound. That's how you all sound when you dog on androids. That's what I hear.
Or only
All right.
backwards.